Hello everyone, and welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Rula Adib. I'm a Senior Principal at Geosyntac Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of SERDP and ESTCP by Dr. Herb Nelson, followed by a list of upcoming webinars in the series. After Herb's opening remarks, we will transition to the technical portion of the webinar. Today's event features two presenters who will share with us recent advances in the classification of underwater munitions near a water-sediment boundary. First, Dr. Aubrey Espana from the Applied Physics Laboratory at the University of Washington will provide an introduction of this ESTCP-funded project on the classification of underwater munitions. Second, her colleague, Dr. Tim Martin at the University of Washington will provide the first of two technical presentations detailing the results of their study. We will pause following Tim's presentation to answer some of your questions. Following this first Q&A session, Aubrey will give a second technical presentation focusing on the classification and performance of the tools that Tim and Aubrey will discuss with you. We will conclude the webinar with an interactive Q&A session including both of our speakers. Today's broadcast will be listen only. You may submit your questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit your questions well in advance of the Q&A session. On the slide, we have provided a few suggestions in the event that you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference line. If you continue to have problems, please submit a comment using the chat box in the lower left corner of your screen. With that, I would like to introduce Dr. Herb Nelson, who has been serving as the SERDP and ESTCP Program Manager for Munitions Response since 2007. Prior to that, Herb was a research chemist at the Naval Research Lab in Washington, where his work focused on the dissection and classification of buried UXO. And with that, I turn it over to you, Herb.
Thank you, Rula, and I would like to add my welcome to you all, along with Rula, to the participants in our webinar here today. So my section is for those of you that have only are new to us or have not been coming to these webinars regularly, a little overview of SERDP and ESTCP. So we are two programs, as you see from that slide. SERDP, which is the Strategic Environmental Research and Development Program, is a long-running program established by Congress years ago that is a partnership between DOD, DOE, and EPA. It is the research and development part of the program, the pair. And as you see on the last two sub-bullets on this slide, advanced technology development to address near-term needs, and in addition to fundamental research that we work on to impact DOD environmental management problems. The companion program, ESTCP, which stands for the Environmental Security Technology Certification Program, is a demonstration validation program in DOD words. And here we demonstrate innovative, cost-effective technologies. Many of these technologies were developed in SERDP, but not always. Some of them come to us fresh from other development funding sources or sometimes internal to our company funding sources. And this program is really meant to transition technology out of the lab into the field at a DOD site. And the output of ESTCP demonstration is a cost and performance report in which we gather cost information and performance, of course, just as it says, and compare it to the status quo. So we are divided into 5 program areas at the SERDP and ESTCP. Energy and water, which is a ESTCP program only demonstrations validation in that one. And then the other 4 program areas that are listed here. And of course, the subject today is Munition Response, program area number 3. Although I think of it as number 1. So we have in the past been involved with munitions on land heavily. Those of you familiar with our program know this has been about a 15-year effort, which we really are at the end of, and in fact have not had any new starts in munitions on land in a couple of years now. So we transitioned the program into munitions underwater. And these areas that we're looking at or focusing on are both wide area and detailed surveys. So some of the presentations today will focus on that, of course, you'll see. Recovery and disposal technologies for munitions underwater, and then just generally characteristics of them, their environment that they're in, the clutter field, and mobility of munitions. So those are the three areas we are focusing in. Before we get to the presentations today, here are the next three in the series. You can see we have them every couple of weeks. And as we go through, we rotate the program areas. So the next time there will be a munitions one is in a couple of months. These are the ones that are upcoming, though. And now I'll transition back to Rula, who will introduce our speakers.
Take over.
Great,
So hi, good morning and afternoon, everybody. Again, I'm Aubrey Espana, and Tim and I are going to be talking to you today about recent advances in the classification of underwater munitions near a water-sediment boundary. Okay, let me start off by giving you an agenda for the next about 10 minutes or so. So what I aim to do here in this first introduction is to give you a big picture view of this project. I'll start off introducing you to all the team members that are involved with this. I'll walk you through the technical problem and why it's so challenging, take you through a little bit of the big picture view of our technical approach to this. And in here you're going to see that we have this 5-year integrated plan that has 2 projects that are going to be advancing in parallel to each other, one funded by SERDP and one by ESTCP. Then we're going to go into the project objectives specifically for the SERDP side of the research, and that will be the focus of the remainder of the webinar, in which you'll see 2 technical presentations by myself and Tim Marston. So I'll give you a roadmap for the rest of the webinar there. And then just to encourage everybody to stick around through the whole thing, I'll show a couple of spoilers that you'll get to see throughout these technical pieces, and we'll be explaining the significance of these throughout. So the project team, we have an array of physicists and signal processors that are involved in this project. We're led by Dr. Steve Cargill, who has expertise in target scattering. Myself, I also work in target scattering, specifically with finite element analysis of the acoustic response of these things. We have Dr. Jack McLaughlin, who is an expert in signal processing with applications to target detection and classification. Another physicist on the project is Dr. Kevin Williams, who also studies target scattering and at-sea field measurements. And then finally, Dr. Tim Marston, who is funded separately but has collaborated very closely with all of us in this work, and is an expert also in signal processing and being able to reduce the sonar data to relevant data products. Somebody else who I would like to acknowledge but is not listed on this slide is a new postdoc to this team, Dr. Dan Plotnick, and he was an integral part in specifically the classification and performance side of this work. So again, Herb kind of gave you a brief introduction on the technical problem we're trying to solve. What we're trying to do is deal with this problem of discarded World War II era munitions. So these are posing a hazard to both the environment and public safety. So the contents might be leaking out into the environment, or in addition to that, you have the public has now been able to access areas that they weren't previously able to. And so you now have this increase in water sports and public coming into contact with munitions. So there's this need for assessing and predicting the locations of munitions relative to the seafloor in cluttered environments especially. And so one of the methods that has established itself as a very useful means to do this is acoustics. And in these pictures on the right side, these kind of give you a little hint as to why we like to use acoustics. Number one, you might be going into an environment where you have very poor visibility. And in those situations, your optical methods are not going to work. And so you need to use this acoustics, which is not affected by poor visibility. Furthermore, you could have the situation in the bottom right-hand picture in which you actually have a munition that is completely buried in a mud environment. And so in these situations, the sound can actually penetrate the seafloor, and you have the ability to detect objects that are buried. Now that being said, we still face a lot of challenges when it comes to trying to use acoustics to do this. And some of these are listed here on this slide. So the acoustic response that you measure from these objects is affected by many different factors. You can have operational choices. So what path is your vehicle going to take? How high is it going to be off of the seafloor? There's environmental factors that will affect this. Is your object partially or fully buried? Do you have some strange bottom topography that's causing problems? Are there a lot of biologics? And then finally, the processing tools that we use. So when you acquire some raw data, what processing are you going to do to create a data product? How are you going to extract the relevant information from those data products? And how are you going to train these algorithms that are going to be able to tell you, yes, I think that that's a target, or no, I think that's just a clutter item. So as you can see, this is a very interdisciplinary chain. And so the approach to trying to solve this problem has been very categorized, and rightly so. You have experts who understand the target physics very well. They might try to pass off some information down the chain. You have people who understand the environment and how sound will scatter from, say, a rippled seafloor like you see in the picture, the red picture on the bottom of the screen here. You have people, signal processors and machine learning people who understand how to train a target recognition system in order to be able to say whether something's a target or not. And then finally, you can come out and get a measure of the performance and how you expect this trained algorithm to perform in the field. But maybe what we need to do is rethink this flow chart. So what we'd like to do is have the physics actually start to inform decisions that are made further on down the chain in the classification side. And so what we've done is try to formulate this problem into more of a performance chain. And so we're going to look at the target in the environment response. So you're going to acquire some raw data, and this really is the tier response. We're going to create some data products, and these are going to be data products that are going to highlight the physics. And we're going to pass this off to the classification chain and see if we can come up with ways to identify and extract the relevant information from these data products that's going to help us to be able to classify something as a target or non-target. So with this kind of general approach and flowchart in mind, here's the official problem statement that we're working on. So the ultimate goal of our work is to deliver a cost-effective, field-tested tow body system with an operations classification package for the detection and classification of munitions in underwater environments. We have a 5-year integrated plan to do this, and it involves 2 projects. The one we're going to be talking about today is the SERDP-funded MR2505, and this is the operations and classification package, which is going to develop and train classification algorithms. The second project is this tow body package, which is an ESTCP-funded project, and it's currently in the design study phase of using a platform, of designing a platform that uses commercial off-the-shelf components. Okay, I don't get too bogged down about the details here, but what this does right here is map out how we envision these 2 projects progressing over the next 5 years. So the subject of the talk today is going to be these green boxes in the center of the page. And again, this is the operations and classification package. So we're in year 1 of this, in which we're developing and training classification algorithms. And we're doing this by using work that was done over the past 3 years, and that's what Tim's going to talk about, is some field experiments and some models we've developed, and how those 2 in conjunction are feeding into our ability to develop and train these classification algorithms. Now in parallel to this, we've got the tow body that is being designed right now. Assuming that a follow-on gets funded with that, the following year we will be in the construction and dockside testing side of things. Meanwhile, on the operations and classification side of things, we're going to do a controlled rail experiment in an acoustically hard environment, which is going to allow us to test out these trained algorithms in a more difficult environment. And then finally, in year 3 of this project, we hope to actually do a full engineering test in the Puget Sound of this tow body design, and that will allow us to test these algorithms out using this tow body data. And all of this will come together in the final year where we'll do a full field test of this with operational classifiers and protocol logistics. So again, just for the remainder of this webinar, we're going to focus on just that top row and specifically that white box, which is Tim's going to take you through that experimental data and models that were developed to inform our current work of developing and training classification algorithms. I'll just say on the tow body side of things, I put up the picture of the current state that it's in that design process. And if anybody has any specific questions regarding the tow body design, I'm happy to take those and take them back to Dr. Kevin Williams, who's the PI on that project, and we can give you more information offline. So here's the outline for the rest of the technical content. What we're going to do is walk through this performance chain. So Tim's going to start off at the raw data side of things, show you some processing tools to create these data products, and then show you results from field experiments and the models and how these two are playing together to help us make advancements. Then I'm going to follow that with the classification side of things and the performance side of things. And I'll take you through a simple example so that you at least have a general picture of what goes on behind the scenes, and then show you some results and where we step back and ask ourselves, how good did we do, and can we do better armed with just a little bit of physics. So here's the spoilers that I promised to show you. What you're going to see in the next 2 talks is number 1, SAS Processing is a great tool. You're actually able to see targets in very noisy environments. Number 2, the models, we've been able to use these to dissect the physics. And it's the interplay of these two together that are allowing us to come up with better classification methods, which you can see the results in the right side there. So with that, I'm going to turn it over to Dr. Tim Marston, who's going to take you through the target and environment response.
Great. Thanks, Aubrey. As she mentioned, my name is Tim Marston. I also work here at the Applied Physics Laboratory, University of Washington. And I'm going to basically give a background information on how we take the raw acoustic information and we extract useful data products for classification. And I'm going to talk a little bit about what those data products are. I'm going to cover some results from recent field experiments, and in parallel, I'm going to show how we're also numerically modeling these results to gain insights both into the physics and also develop data sets that we can use to augment training methods to improve performance of classifiers. So the underlying technology that we're exploiting is something called synthetic aperture sonar. This is a coherent signal processing technique in which we take a sonar and we move it along some predefined trajectory, and we emit pings, and we record the amplitude and phase of the backscattered signals as we move along the trajectory. The raw data that we get out doesn't look like an image, but we can beamform the image in post-processing to create a variety of different data products that are highly information rich because we have acoustic information related to both the image of the object, and we're looking at it from many different angles because the beam width of SAS systems tends to be very large. And furthermore, we can get spectral features. When we think of SAS, we also tend to think of systems that have a wide range of bandwidth. So high frequency in a synthetic aperture sonar context typically refers to the low hundreds of kilohertz. So if you're thinking about, say, a side scan system, very high frequency side scan systems may be over megahertz. For high frequency systems, you tend to be operating at maybe 150 kilohertz. There are some systems that go even above 300 kilohertz, but those are very high frequencies for a synthetic aperture system. On the low end, we tend to see things at in the low tens of kilohertz. Also, we tend to think of SAS in terms of different scan pattern geometries. So the typical scan pattern geometry we use, which is effective from a wide area survey standpoint, is a linear scan pattern. So we move in a straight line. We may do something like mow the lawn, where we take a series of straight lines and we try to cover a large area. And again, the advantage of this is area coverage rate. We also have a different method of processing where we move in a circle around an object. And while this sacrifices area coverage rate, the advantages are you get a much higher certainty about an object that you're scanning around. And more particularly relevant to this case, you can characterize an object to aid in training to help recognize objects that you encounter during an ordinary linear SAS scan pattern. So typically when we numerically model the response of objects, we do that in a circular SAS framework. So these are some examples of data products using these different scan methods. These are just the raw data before beamforming. You can see that they are very difficult to interpret. On the left-hand side, when you see unprocessed synthetic aperture sonar data, it doesn't look like an image. It typically looks like a series of arcs. And the circular scan case is even more difficult to interpret. It's what's called a sinogram. It's essentially the radon transform of the reflectivity map of the seafloor. Now, this is a little cartoon illustrating the beamforming process. There's many methods for doing this, but they all essentially amount to doing a spatially variant matched filter to deconvolve out the response of the aperture pattern that the synthetic aperture array has. And you can see the focused acoustic data on the right. Now, the image I'm showing at right here isn't your standard image that shows the sediment texture, a bright glint, and a shadow, because this is a low frequency image. So we see these bright glints, but then we see trailing information behind the leading edge. And this contains structural information. And that structural information is one of the things we're going to tap into when we generate our classifiers. These are examples of high-frequency synthetic aperture sonar data products. On the left, when you have a high-frequency system, this was about 150 kilohertz here, you get bright glints and you get shadows and you get textural information about the seafloor. In contrast, for the circular scan case, when you use imagery as a data product, you get low speckle noise for the seafloor, and you also get complete outlines of targets, making identification essentially trivial. Now with low frequencies, we're not so much interested in the image, although we do exploit the image to reduce the clutter from adjacent targets, as well as increase the SNR of the signal that we extract. But we're more interested in the spectral response. And what I'm showing here on the left is the isolated raw data associated with a given target. And we care about this because as we move along the linear scan, we're looking at the acoustic response of an object from different rotation angles. So if we take the raw data and we map the cross range to angle, and then we take a Fourier transform in the time axis, we can look at the frequency response of the object. And that's what's shown on the right here, where we have a matrix that shows angle versus frequency. So what we're looking at is we're looking at the impulse response of the object as a function of look angle. And this forms what amounts to an acoustic fingerprint for an object. This frequency response is dependent on the material properties of the object, or potentially the filling material of the object, as well as its structure. And it's also a function of the environment. So this is what a lot of the target environment modeling is attempting to augment, is our ability to understand how the environment affects this frequency response, so we can make classification algorithms that are very robust to encountering these objects in a variety of configurations relative to the sediment, as well as for different sediment properties. Now these are examples of this acoustic frequency response data product, which we typically call acoustic color, for the different scan patterns. So you can see on the right-hand side for the circular scan pattern, we're looking at this object from all angles, from 360 degrees of angles. And so you get a lot of information here. So the angle span, the vertical axis on the bottom right image, spans from 0 to 360 degrees. And you can see a lot of symmetries in this acoustic color data product that can be exploited, or features, maybe resonance features, structural features that can be exploited to determine whether this is a UXO or this is a clutter object. In contrast now, when you're doing a linear scan, because your look angles at the targets are only determined based on the beam width of the transmitter and receiver, which for low frequencies it tends to be pretty wide. So you may have plus or minus 40 degrees with a total of 80 degrees. And these snippets correspond to segments of the circular scan case around the object. So when we want to train an object or generate a template, which is something that we're going to match these segments to, we tend to try to do that in the circular SAS framework so we can compensate for the fact that in reality we don't know what orientation the object is going to be in. And then when we encounter these objects in a standard linear scan survey, we can take these acoustic color segments and now compare them to the templates which have been generated in a circular SAS case. So these are some field experiments in which we experimentally developed our methods for extracting the acoustic information and compare the results to numerical models. And they've all been planned to allow different levels of control over the environment and to vary the environment to see how the environment affects the response of the targets. So we began in 2010 with the Pond X10 experiments, and this used a freshwater artificial lake at the Naval Surface Warfare Center in Panama City. We put 6 targets down and we had a rail system and we rotated the targets and we scanned the targets and we could generate these 360-degree templates for the target response. In T-Rex 13, we were still operating in Panama City, but now we moved out into the ocean environment where we were in salt water. We still had sand, but we used a much larger array of targets and the grazing angles to the targets spanned a much larger range. Then in Bay X14, we moved into a brackish water environment where now we were on mud instead of sand. And frequently, as you can see in the next slide, objects would bury. So if you look at the images on the right-hand column, you can see that objects were either partially buried or completely buried most of the time. In T-Rex 13, we could keep the targets proud frequently just because it was on sand, but we had a different problem, which was that we had a huge number of biological organisms. This is because of what's called the artificial reef phenomena, where if you have a flat, featureless sediment in the ocean and you put down some large structure, biological organisms will flock to the structure for protection because it's like an artificial reef. And so we had lots of fish surrounding the sonar tower, which posed some challenges for the signal processing and subsequent steps. Now this is the rail system that the APL-UW uses. It's over 40 meters long, and it has a sonar tower mounted on it. It has a source and several receivers on a vertical array. The low frequency source tends to emit data from about 3 to 30 kilohertz. And we had a high frequency source as well for the very last experiment in Bay X10, and I will be showing some comparisons between low frequency and high frequency data in some subsequent slides. Now on this slide, you can see some examples of raw data and the corresponding beamformed imagery. And the point is to show that because SAS is what I'll call an integrative technique, which means that we're going to be looking at the acoustic information from signals as we move along a trajectory, we can average those signals. This is essentially what the match filtering operation is doing. And for scatterers that are non-stationary, such as the swim bladders of fish, these tend to average out, whereas the stationary signals from targets tend to add coherently, and as a result you get a suppression of noise from things like fish, and this actually allows you oftentimes to see through occlusions as well, whereas the fish tends to just dissipate. And you can see that particularly for the middle image on the left-hand column, where you can barely see the front row of targets, where on the right-hand side, after beamforming, you can see the front row of targets very easily, and in fact we have a very large SNR. And again, the point of these low-frequency images is not to generate a beautiful picture, but to show regions of interest where we are interested in seeing, hey, there's an object here, is this a UXO or not a UXO, and then extract those spectral features. And in that spectral feature domain is where we're going to find the discriminatory features that allow us to determine if it's a UXO or a non-UXO. This is a comparison of a high-frequency and low-frequency data product for the BayX experiments. On the left-hand side, this high-frequency data product shows texture. You can immediately see some of the very proud targets. You can see glints. You can see shadows. You can even see the cables that are stretched across the target field. These were implemented to allow the divers to place the targets because the visibility in this case was so poor that oftentimes the divers couldn't even see their hand in front of their face. So the high frequency is fairly intuitive to interpret. However, as you'll notice in the bright red box at close range, we had a large array of targets in this region, and it's virtually impossible to spot where the targets are. And this is because the backscattering from the sediment is very strong. There may be little to no shadow because the targets are either completely buried or only partially buried. In contrast, when you look at the right-hand image, it's trivial to identify where the objects are. This is because the backscattering from the sediment is much less for the low frequency, and the objects show up much more brightly against the background. This means that low frequency SAS data is very useful for something like region of interest detection, where you want to look at an image and you want to determine where the potential objects may be that could be UXOs. You can see there's a bright set of noise at about 15 meters. This is not actually a target. This is an artifact of the fact that the research vessel was behind the rail, and there was a main lobe for the receiver that pointed out in that direction. So you can ignore that. You can ignore that artifact, but you can see that it's almost trivial to identify where the location of the rest of the scatterers in the scene are because of the brightness and the contrast with which the targets show up relative to the background. Now this is showing some of the spectral features that you can recover from the data. Now these are actually pieced together from a series of linear scans, but what you can see is that each of these objects, which are shown in the inset image at the top left, these are a steel artillery shell plus a steel replica and an aluminum replica. And you can see that many of these spectral features are different, particularly for the aluminum replica, because of the different material properties. And these are things that we're queuing on when we're doing classification work. Now in parallel, there's a lot of efforts to do numerical modeling. There's a couple of reasons we're interested in numerical modeling. First of all, when you think about all the different configurations that a target can have relative to the sediment and all the different sediment types and all the different scan patterns which can change the grazing angle, there's a very large parameter space over which the algorithms that we use to classify have to be cognizant of the changes. And as a result, from an experimental standpoint, it would be very difficult, especially from a cost perspective and a time perspective, to try to experimentally determine the acoustic response for objects in all these configurations. So there's been a lot of effort to make rapid computational estimates of how the response of objects are affected by the environment so that classification algorithms can be made very robust to these changes. Additionally, by studying the physics closely on this side of things, we can actually gain insight to determine where the critical information is that separates things like UXO from objects like rocks or bricks or metallic objects like pipes or things that we are not interested in cleaning up. So one of the ways we're doing this, one of the ways that Steve and Aubrey have developed to do this very efficiently, is to begin with a finite element model in the free field. And by the free field, that means they simulate a scatterer like this bullet here in an infinite vacuum or in an infinite volume of water. So it's the only scatterer present. And then they look at the acoustic response as a function of arbitrary orientation. So they have a complete response of the object for any orientation in this free field environment. And then they insert this using ray theory into an environment that now includes the sediment. And so these different ray paths that are illustrated here on the right-hand box describe the interactions between the source, the target, and the sediment. And they add those in to this free field model to generate the effects that you're going to see when the object is in the environment. And this is an example of a comparison between experimental data collected in an environment at different grazing angles and different burial states versus the model calculated using this target in environment response or tier response. And the thing to take away here is that this target environment response actually tracks a lot of the features very well that we measure experimentally. So you can see these modes here at about 10 kilohertz and 60 degrees off broadside on the top left. These are flexural modes. You can see how the coupling to those modes actually changes as a function of grazing angle. So if we moved now to a range of 5 meters, our grazing angle is going to be steeper because we're at an elevation of about 3 meters. This changes where those flexural modes get excited because of the acoustic coupling. You can also see that these features are changed when you get to a different burial state. Now if we look down at the data, we can see that these modes change in location in a way that matches the model. And we can also see a change in the nulls as well. So if you look at the broadside scattering, which is about 90 degrees, you see a rather broad null at about 20 kilohertz, which gets filled in when you move to the closer grazing angle. And you can also see another null forming at about 25 kilohertz in the buried case at 5 meters as well. But you can also play some interesting games with the models that we can approximate with the real data as well. And one of the things we're looking at is isolating the full response of an object, which includes the reflection off the surface as well as the excitation of modes because the object is elastic. And we can artificially, in computations, set the objects to be perfectly rigid, which means now we're going to be ignoring all the elastic effects. We're not going to let the object vibrate or flex in any way. And we can look at the backscattering in that case. And that's what's shown here on the right. And you can see there's differences. This is because we don't have modal excitations anymore. Now what does this give us? Well, this gives us insight, first of all, into, because oftentimes the backscattering from the surface can be very strong, we can learn various things about the about target features just from the shape. So for example, when you see the scuba tanks and the howitzers at the bottom, the broadside backscattering response is very narrow. This is because the width of that peak is related to the width of the object itself. However, if you look at the top two targets, they're very similar from a shape standpoint, and it may be virtually impossible to discriminate between these targets. And an analogy may be perhaps if you have an object that has a filler versus doesn't have a filler, they have the same shape, but now you're going to want to cue into elastic modes because the shape may not have enough information just to determine that. However, you could use the shape information to determine if this is a bullet or a rock, say. And one of the ways that we're going to be doing this in practice, and Aubrey will talk about this more, is the rigid response tends to occur early in time. But the elastic response, because you're exciting modes, tends to trail behind the target. So if you do an early time, late time separation and then look at the spectral responses for each of these, then that actually separates these two physical components of the scattering response, and you can feed both of those as data products into the classifier and actually improve results in many cases. So that's a little teaser for Aubrey's talk, which is coming up next. But in conclusion, the synthetic aperture sonar data products are highly information rich. This is because you're looking at the backscattering response over a very wide variety of angles. And furthermore, when we look at low frequencies, we can excite structural modes. And this modal excitation has a lot of information which has discriminatory power. And additionally, on the numerical modeling side, we gain insight because we're looking closely at the physical scattering mechanisms that help us determine what may be useful features during the classification process. And that wraps it up for my talk, and I'd be happy to field any questions.
Great. Thank you, Tim, for a very informative presentation. I would like to remind our audience to submit questions by using the chat box on the left-hand portion of the screen. We have received a number of questions for Aubrey and Tim, and I'm just going to start with a quick question for Aubrey. On your 5-year integrated plan slide, you mentioned acoustically hard environments. Can you please elaborate on what the characteristics of these environments are?
Yeah, so what we have planned, our acoustically hard environment is going to be, we're going to have targets deployed out there, and we're going to throw a bunch of clutter items in very close vicinity to them. So rocks, lobster traps, oil drums are going to be kind of obscuring targets very close to them, making it challenging to separate out the targets, and that's going to be a real test on the system. Alternatively, you could envision an acoustically hard environment as being one that has a lot of coral heads or basically hard natural things that are out there that are going to have a large acoustic response that could mask any potential targets.
Thank you, Aubrey. Tim, we've received several questions from Cal EPA and Federal EPA. I'm going to pose them to you. For starters, does SAS work when targets are corroded or are of weird shapes?
Great, that's a good question. So the idea of beamforming for synthetic aperture imaging is very general, which means that especially for targets that may not have long resonances, you can image objects of arbitrary shape, and you may get a very high resolution, well-focused image. I think the real question is, when you're trying to look at these spectral features, does, say, corrosion on the target affect the acoustic response of the target? And the answer is yes, and I still think that needs to be looked at very carefully, because when you add corrosion to a target, the effect is you're going to cause probably you're going to add damping. So when you have these modal excitations, if you have corrosion on the outside, that may change the quality factor of some of the resonances that the target may have, or how it flexes. So these are things that will eventually need to be modeled and included in that modeling effort. And that's one of the things that modeling is useful for, is you can potentially add that kind of information to a target. When you're dealing with low frequencies, corrosion effects on an object tend to be much smaller than a wavelength, so they can potentially be modeled in the finite element analysis framework.
Thank you, Tim. Questions from Federal EPA. We have used acoustics for bathymetry, but not as a main tool to detect underwater munitions. We use geophysics for detection of underwater munitions. Are you envisioning to develop the tools you discussed as an alternative to geophysics or to supplement it?
Well, I think if you were to envision maybe the ideal munitions response program, that all of these things are potentially very supplementary. For example, you can get a lot of really good shape information or acoustic response information from acoustics, but one of the major classification features is going to be, is it metal or is it not metal? And that's something that magnetics would be useful for. So I see these things as being very complementary. One of the things that we're looking at, for example, integrating onto the towfish that Aubrey showed, is the bottom object scanning sonar, which allows us to look into the sediment and generate high resolution images of objects underneath the sediment. And so that shape information for objects and the spectral acoustic information, I think, would go very well with an electromagnetic induction or a magnetic sensor. One of the advantages, of course, of an acoustic system is that you can get quite a large range potential. So if we can see through the sediment, particularly in muddy environments, having a long-range, low-frequency acoustic system would allow us to identify regions of interest and get that spectral information for objects that are buried. So I see wide area survey and survey times as being an advantage of acoustics. But again, I think all these systems would be highly complementary.
Thank you, Tim. Can you comment on the cost of acoustics compared to geophysics-based tools?
That would probably better be deferred to Kevin, who is actually marking up the costs for developing a towfish system. But again, we're looking at commercial off-the-shelf type things. So the BOSS system from EdgeTech is one of the systems that we are looking at using. And I believe that runs at a couple $100,000, but I'm not entirely sure.
Wonderful, thank you. Another question from EPA, how does concretia on the projectile underwater affect the hybrid model, and how does corrosion of the projectile affect the model?
Great, that's another very good question, and I think I answered that a little bit in my first question when I talked about how this is going to affect the modal excitations of objects. I don't think there's been a lot of work so far on the numerical side modeling those effects, but I think eventually they will be done, because again, that's going to be something that's really prevalent. Something that I think would strongly affect a target would be if it was corroded to the extent that now it had a hole in it. Because that may change, it may cause a breathing mode, or it may change how it flexes. So if you have a large amount of corrosion, something that severely affects the elastic response, then that may really affect things. However, as long as you preserve a lot of the shape information, then the spectral content associated with the shape will still be present. And again, that's one of the discriminating features, even in this frequency space, is how those broadside glints are distributed in angle as a discriminatory feature.
Thank you, Tim. Can you please tell us how deep SAS penetrates, and how is the depth determined from the response?
Sure. Well, first of all, how deep SAS penetrates is primarily a function of both the wavelength and the sound speed in the sediment. So if you have a very fast sediment, or a sediment that has a high sound speed relative to water, then you're going to have a critical angle, and the critical angle is going to depend on the sound speed in the sediment. So for example, if you're in sand, the critical angle tends to be at about 30 degrees. So beyond 30 degrees, anything that penetrates under the sand is called an evanescent wave, and you really don't get a huge amount of information in the evanescent region. There is some there, but it's not primarily what we're interested in looking at. If you're in mud, however, and the mud tends to be near the sound speed of water or less, then you can look through the mud throughout almost the entire swath, and the penetration depth is going to be related to the wavelength of the sonar. So at high frequencies, you're really not going to look into the sediment at all. And at lower frequencies, you're going to get maybe on the order of several tens of wavelengths into the sediment. It will some degree depend on whether you can image down there, depending on how much signal power you put out in the transmitted signal.
Great, thank you. How well does the ray model work when predicting the scattered field from a buried target?
That's also a good question, and it depends. Actually, when I talk to the modeling guys, it sounds like the hardest place to model is actually partial burial. So if you're completely buried, then you can model that pretty well. And if you're completely proud, then you can model that. And in fact, when you're a long ways away from the interface and you're buried, then the problem even gets easier. So the primary challenges for modeling happen to be when an object is only partially buried, or perhaps oblique, which means it's tilted and it's partially buried.
Thank you, Tim. Can you discuss how you envision these tools to be transitioned for non-research users or for ultimate end users at DoD?
Sure. So the idea behind this low-frequency SAS in particular is that it would not be implemented in a way that's all that different from, say, an underwater survey that you may conduct using something like an EdgeTech high-frequency side scan. You would just get a different data product. So with a low-frequency system, you may have a towfish, and you may have a low-frequency system that's looking out to the side, or you may have something like the BOSS that is more essentially like a low-frequency multi-beam that looks through the sediment looking down with perhaps out to 30 degrees, grazing angle on both sides. And you'd make a survey using that kind of standard method, mowing the lawn, and you'd have a detector that detects perhaps energy, and then you'd have a region of interest extraction. This would all be done automatically. There are techniques for doing this. You can extract regions of interest and then look at the spectral features. And so an operator may see a flow of acoustic information on a screen. There may be a blob with a little box around it that says, this object has some confidence level that this is a UXO, and the way I envision it, at least with a BOSS system, would be you could zoom in on that object and look at, say, a three-dimensional view of the target, because BOSS generates volumetric data. Or if you had a side-looking low-frequency system, you could zoom in on the object and get a operator-based, more qualitative assessment of whether or not this is a low-frequency or this is a UXO or not. But you would have some little number on there associated with the classification confidence that this is or is not a UXO.
Thank you very much, Tim. At this point, we're going to hand it back to Aubrey for the second part of the technical presentation. There are questions that we haven't gotten to yet, but we'll save them for the final Q&A session. So back to you, Audrey.
Great. Thank you, Rula. All right, so let's go into part 2 here. And here I'm going to be talking about the classification and performance side of this problem. And so agenda for this, again, just to recap, Tim took us through the first piece of this performance chain that we saw. So the raw data, the processing tools that we use to create these data products, and then showed the results from some experiments and the models and their significance. So on the classification side, instead of just throwing up results that we've done and trying to convince you and say in words why these are significant, you're going to have much more appreciation for the significance of those results if I give you just a little, big picture, simple view of what goes on behind the scenes when people say target classification. So that's my goal in this first part, is to show you a simple example so you can get a general picture of what happens in each of these processes, the feature extraction, the nonlinear kernel, and then training a classifier. Then we'll actually go out and show you results for the classification study on real data. And we'll step back and look at the performance and ask ourselves, all right, how well did we do at training this classifier? And is there, with a little bit of physics, can we somehow do better? Can we try to optimize the performance of this? All right, so step number one, and full disclosure here, I'm just in this simple example, this is only one particular way you could look at this problem. And the particular one I'm going to show here is going to be a relevance vector machine. And so step one in this process is going to be the feature extraction process. And what this is doing is you're essentially taking these data products and you're asking yourselves, all right, how can I extract information from this that has the potential to discriminate between targets and clutter items? So when we say feature, these are going to be derived from measurable descriptive target characteristics. Ideally, they're going to provide a clear separation between a target and a clutter item. Now, with low frequency, as you saw in Tim's previous talk, we focus a lot on the low frequency acoustic color data products. Before I jump into those, I want to show you an example of what features could be for a high frequency SAS image, because this gives you the ability to, it's a lot more intuitive than what a feature is for the low frequency side. So for the high frequency SAS images, which an example is shown here, these could be geometric characteristics, so maybe mean highlight or mean shadow. So the difficulty is that this stuff, typically you need a fairly large set of data in order to do the training and testing procedure. And so you're going to need to be able to extract these features automatically. And so that's where the environment starts to cause problems. You can see in these examples here of when you try to automatically identify what these mean highlights and mean shadows are, it gets confused with the ripple pattern of the seafloor that you see in the background there. So this is a very difficult thing to do. In the low frequency side of things, okay, so here again, we're not creating images of the target like you do with the high frequency. What we're doing here is dealing with this acoustic color information. And so with these, what you would do is you're actually doing template matching or a pattern recognition. So for this very simple example, what I'm going to show you is I have 4 different data products here. These are just little snippets of a full acoustic color. And what you do is you're going to take each of these data products and you're going to compare it to itself and then the remaining 3. And you're going to populate this design matrix here. And so in an ideal world, you're going to, and when I say populate this design matrix, you're going to have some sort of measure of the similarity between each of these acoustic color data products. So in the ideal case, number 1 is going to look exactly like itself, and so you're going to get a 1 in this upper left corner of this design matrix. And it's not going to look like anything else, so you're going to get zeros everywhere else. Now, in reality, what happens is number 1 actually looks a little bit like number 2. And so you end up with a positive non-zero number off diagonal here. So just in this simple example, it's these non-zero off diagonal components that have the potential to cause us problems. When people use the terms like nonlinear kernel, all we're doing here is this is a method to try to increase the separations between the targets and non-targets. Okay, so we've built our design matrix and we've applied a nonlinear kernel. Now what we need to do is we need to try to identify the most discriminatory features, all right? And so this is what the relevance vector machine is going to do, is it's going to go out and look at this kernel and it's going to say, tell me what are the most relevant feature vectors. An example would be this top row here in this design matrix. So when I say relevant feature vectors, I mean those that are going to have the most discriminatory potential to say, yes, this is a target, or no, this is a clutter item. And this is the process of training the classifier. Now, you wouldn't just train a classifier and then pass this off to somebody and have them take it out in the field. What you need to do is you need to test it out. And to test it out, you need to have some set of data, and you've got to have the answer key in your back pocket. So you've got to know, okay, in this data, I know that that's a target, that's a clutter item. And you're going to take this, armed with this set of relevant feature vectors, and you're going to say, all right, let me put you to the test. Tell me if this, in this data set, which ones are the targets and which ones are not the targets. So it's going to go through and it's going to build another design matrix. It's going to compare and come up with this measure of similarity between each of the data products and assign a number to it. And then you're going to go out and check the answer. And you're going to say, oh, wow, you did good there. That one was indeed a target. Oh, nope, here you were wrong. So that process of doing that is how you build your performance estimation curve here. So this is a receiver operator characteristic curve, or a ROC curve. And I want to spend a little bit of time explaining this because this is something that is used a lot, is a terminology that's used a lot in this type of classification. And so what the receiver operator characteristic curve is, it tells you, it gives you a measure of how often you correctly classify a target as a target and how often you're wrong. So on the y-axis here is your true positive rate. And again, that is how often you've called the target a target. The x-axis is the false positive rate. That's how often you have incorrectly identified a target, a non-target, as a target. There are two extremes that I point out here. The diagonal, the dashed line that goes along the diagonal, that's the case where you've done no better than a coin toss. And then the ideal situation would be this thick dashed line that goes straight up to 100% and over. So in that case, you have correctly classified all the targets as targets and you have no false alarms. And so what this plot is doing is it's giving you a useful measure for a cost-risk analysis. So the false alarms, as you can imagine, it's very expensive to go out and remediate one of these things. And so you want to reduce your false alarm rate. But on the risk side of things, if that comes with the added risk of potentially not classifying a target as a target, that of course then gives you your risk as you move forward. Okay, so I gave you just that simple kind of pictorial view of what goes on behind the scenes. Let's now go through an actual classification study using the T-Rex 13 data that Tim showed you a little bit about. So let's walk through this whole chain of raw data to data products and then through the classification to performance side. And so on the bottom left here, I show you a picture of the raw time signals. We've done the processing to create full acoustic color templates of those, and during this experiment, we had 90 acoustic color templates. Now our data products are, we're going to take these full acoustic color templates and we're going to section them off into 18 uniformly overlapping sections. Now before I move on, I'm going to stop here. If you were really paying attention to the first technical piece, you might notice that the raw data looks like it came from a circular SAS. However, if you remember in the T-Rex experiment, we actually used a linear SAS system. Now, we didn't get to, in the interest of time, we didn't go through the details of how you build an acoustic color template, but the idea is that you would put a target out, you would have divers manipulate it, you'd run the linear rail to acquire a section of linear acoustic data, the divers would go out, manipulate the target, you'd run your linear rail again, and in that way you can stitch together this full acoustic color response. So if you already had these linear rail sections, why not just use those? Why did we go to the trouble of stitching together the full response only to then break it up again? The reason being is that having this full acoustic color template now gives us the power to start to investigate other things. So for example, here, what I'll end up showing you is the 18 uniform sections, but another thing you could do is, well, what would happen if let's pretend I had a beam width that gave me a full 90 degrees if I did a linear run. So I could take this full acoustic color template and divide it into 4 sections and then say, how does that affect the classification? So you have the power to do investigate a number of different parameters as you move forward in this classification side. Okay, so let's go ahead and take these 90 acoustic color templates, which have been divided into 18 sections, and those are going to be our data products. So we have a total amount of 1,620 data products at our disposal for our training set. So again, we're going to take each one of those and compare it to itself and all others. We're going to assign a number for the measure of the similarity between the two of these, and we're going to populate that design matrix. We're going to do the nonlinear kernel, and then run the relevance vector machine to tell us what are the most relevant discriminatory features out there. So again, if you remember, I had mentioned that it's potentially these non-zero off-diagonal components that can cause problems. Now, we need to test the classifier to ask ourselves, okay, how well has this trained algorithm done? So to come up with a data set in order to test this, what we did was we took the same 90 acoustic color templates, but we added some noise, and we also downsampled in both the frequency and angle space. So we kind of degraded these acoustic color templates. And then we went ahead and sectioned them off again into 18 sections, but this time it was randomly sectioned. So what we've done here is try to create kind of a pseudo testing set that we can go off and test this trained classifier. So again, we're going to take that and we're going to compare it to each of our training data products. And we're going to get a measure of the similarity between the two. And then we're going to check our answers because we know which ones of these were actually targets or non-targets. And so here's our ROC curve that we get after doing this. And so what you notice is it's not necessarily stellar. It's not the best performance, correct? So our question was why? Can we do better? And so the first place we looked was to go in and say, okay, hold on. What are these relevant vectors? Where do they come from? What do they correspond to in the actual acoustic response of these objects? So it turns out that if you go back to the data products and you look to where these relevance vectors are coming from, a majority of them are being derived from broadside and end-on responses. Now, you may recall that Tim had pointed out that we had started to dissect the physics using the models. And what we had learned when we did that, specifically we did that rigid separation. So we modeled a rigid target, which essentially just gave you the scattering to the shape of the object itself, and then the elastic side of the object. And so when you compared those two, you saw that the shape actually dominated the broadside and end-on responses. And so it makes sense then that if you had a classifier that was really just keying in on those broadside and end-on responses, it's not going to be able to distinguish between objects that have similar size and shape. So the question is that we pose to ourselves is there a way that we can approximate this in a real data, from a real data standpoint? So with the models, we can do this exactly, and Tim talked about that. But with the data, how would you pull off this separation? And so it turns out that in the most approximate sense, the shape information is really contained within the early part of the time signal. And the elastic information is contained in the late part of the time signal. And intuitively, this makes sense because when a target is ringing or you've excited these resonant modes of it, it's going to be ringing for a long time. And so that's the elastic stuff that shows up later in time. So what we did was took all of that T-Rex data and divided it into this early time and late time. And we created acoustic color data products of those. And then we passed those through the whole chain again. So raw data to data products, passed it through the whole chain, the feature extraction, nonlinear kernel, and ultimately came up with our ROC curves there on the right side. So what I'd like to do is plot all of those together on one plot here. And so the red curve is what we had originally in that first step through the chain where we used the full acoustic color data products. The green curve is the result of using just the elastic only information, so that late time only. And you see that it actually looks better. We've done better at our classification when we use that. Whereas the shape, using just the shape information, actually performs worse. Okay. So these are results that were done about a month ago, so some more recent results. What we tried to do was, from the target physics standpoint, we know how important the elastic information is. But the reality is some of that stuff could potentially be covered up depending on what environment you're in. And so if you're in a noisy environment, maybe that elastic information is not going to come through. And if you have a classifier that's trained solely on elastic information, could this potentially hurt you? And so to answer that question, we went in and started to repeat this study using different levels of noise. Right? So on the left side is a low noise environment, which would be kind of equivalent to like a medium sand flat interface. The center is more of a coarse sand environment, and then the final right side is a gravel environment. And so we did the elastic only, the shape only, and then also the normal full response that we put through. There is an additional curve on here, which is the black curve, and there's a lot of details that go into get this that I'm not going to go into here, but the point is that based on what you've learned from separately putting these shape information and elastic information through and then the full information, if you take that information and do kind of a voting scheme to combine it together, you can produce this black curve right here. And so what we learned in doing this study is that the elastic only information is best at these low noise levels. Again, that's the green curve on this left plot here on the bottom. In the middle plot on the bottom, the black curve is the best. So this is kind of an intermediate noise region. And here you can see that in separating out these three, but then combining that information together, we've done the best in that situation. And then finally on the far right side, this would be the high noise environment. You really needed to use the full acoustic color information. Now I will say that recently what's been done now is we've made improvements to this method and can now consistently produce better curves using this kind of black curve, this separating the full, the shape, and the elastic, and combining those three together can consistently produce better results over a wide range of noise levels. So the conclusions for this final technical part here, again, I tried to walk you through just a simple example to try to give you a picture of what goes on in this classification side. But then I jumped to the performance estimation study that we've done on a real set of data. And in the initial case through, we had a difficult time distinguishing objects that are similarly sized. By using the physics, we were able to, the physics that we learned from the model, we could actually separate the shape and elastic information, and we can approximate that in the data by doing an early and late time separation. And then finally, it was the combination of these two. We were able to then come up with improvements to the classification method. So I just want to end on this final slide to bring it all back together into kind of this 5-year integrated plan. And so again, what you saw Tim and myself talk about today was the SERDP funded side of things, which was the green boxes here. So it was the operations and classification package. And specifically that white box in the left was kind of the field experiments and the models that are informing our ability to develop and train these classification algorithms. And then again, in parallel to this, on the ESTCP side, we're in the design phase of a tow body package that is, we hope to progress in parallel with this SERDP project that we spoke about today. So with that, I will end.
Great. Thank you so much, Aubrey. If you guys would like additional information about these projects, Aubrey and Tim kindly included a link to the SERDP and ESTCP webpage with details about this project. With that, we're going to move to our second and final Q&A session, and we've received a number of questions for you, Aubrey. Can you please tell us what computational platform you use to calculate the FEM elastic target response? And can you also tell us how long it takes? And this is a question from Lawrence Livermore National Lab.
Yeah, okay. Yeah, so I do all of the finite element calculations on, I've got 64 gigabytes of RAM, and it's a Mac system. And to build, the beauty is that what I've done is on the finite element side, all you have to do is build the free field response. And so therefore I don't have to do a full three-dimensional target in the environment computation, which would be much more costly. So doing just this free field response in a matter of days, I can have that all calculated, and then I pass it off to Steve, and he handles getting in the environment side of it. So it really is on the order of days to do the free field response, and then Steve moves forward and can do any SAS path that we want to simulate. He can handle with his propagation side of the model.
Wonderful, thank you, Aubrey. A question from Cal EPA. Can you explain why elastic is better at low noise and full is best at high noise? What physical processes are involved?
So I think what's happening is you can excite a lot of these modes, a lot of them can be very strong, these elastic modes. And it's the interplay of this elastic and shape information. They actually can interfere with each other sometimes and produce and result in a full template that maybe has some peaks and nulls that we're kind of masking some of this response. So it's a very, very complicated interplay of these two together. And so in terms of when the environment is again a low noise environment, then it's very easy to see these elastic features. They're much more easily visible, and they're ringing, and they do for a long time. Whereas when you get into a noisy environment, sometimes these features can be masked, and so you're going to maybe need to key off, make sure that you still have that shape information in there. Because again, if you remember, that shape information still produced a very strong effect at broadside and end-on. And so in those high noise environments, you still need to have some way to be using that shape information.
Great, thank you. Another question. Are you aware of any semblance or stacking methodologies which could improve SNR and matching capabilities?
I actually I'm not sure that I can answer that.
Can I chime in here a little bit,
Yeah,
Aubrey?
chime in, Tim. Yeah.
Yeah, when it comes to improving SNR, that a lot of that has to do with how you process the data at the front end. And one of the things you want to do, for example, when you're isolating the acoustic signal, it's the ability to isolate that acoustic signal in the spatial domain that really gives you your boost in SNR. So how well you can do that plays a big part. And there's different ways you can focus the data to draw out, for example, elastic information. One of the problems with standard synthetic aperture sonar imaging is that the point spread function associated with a scatter in an image varies as a function of range, but when you have elastic information, that concept gets destroyed because the elastic information has the same range delay information as the object, however, it has an associated time delay. So there's different methods that we've developed to deal with that problem to maintain a high level of focus of the ringing acoustic information that allows you to isolate that up from the surrounding clutter. Additionally, there's methods that you can use. In fact, there's a pretty good paper out there by a guy named Alan Hunter on wavelet shrinkage that allows you to determine where in the regions of synthetic aperture images you have coherent information versus incoherent information. And resonant information tends to be coherent. And this gives you a good starting point for generating the spatial boundaries that allow you to isolate the acoustic signal and improve SNR. So on the front end at least, that's where we get a lot of our gains, and that's one of the things we're working on. Of course, we're always looking for, we're always working on methods to improve SNR so that we hand off the classifier better data.
Thank you, Aubrey and Tim. Aubrey, another question for you, please. Have you performed a classification study using model results? And if you have, how does it compare to the results shown here using real data?
Yeah, that's a good question. So in the initial push through, when we used the full acoustic color data products, and you saw that we built that design matrix and kernel, what we did there was there were a few targets that we swapped out the real data and put in the model data. And again, I believe that the performance was, and Tim, if you remember differently, you can correct me, but I believe the performance was very similar. What's being done right now is Steve is actually simulating all of the T-Rex data. So he's generating the same acoustic color templates for every one of the targets that we did in that. And we're going to walk through this whole process using model data. And so that will be something we should be able to answer in the near future.
Wonderful, thank you. Can you tell us how much data you need to effectively train a classifier?
Yeah, that's a difficult question because there's not really a definite set. And so what I would say is that you want to make sure that you have a set of data that's large enough that you realize you're going to have to divide it into a training and testing set. And then number two, you want to make sure that it's going to be representative of the concept of operations or the environment you're going to be going into. So because if you have a training set and you've trained this classifier, and then all of a sudden you take it to a different environment and there's something completely different going on, then you wouldn't expect it to perform well. So it's more a question of being able to have a good representation of where you expect, what you expect to encounter when you go out in the field.
Thank you, Aubrey. How long does classifying a target take using your proposed approach?
Okay, so classifying a target, if you've already, to go through the whole process that you saw here, from training a classifier clear through to testing, that's on the order of days. If you've already got your trained classifier and you want to now just put some data through it to get an answer, that's on the order of minutes.
Great. This is really interesting. Are there any other insights you expect to gain from modeling to help inform feature selection?
That's another difficult question. So I think the way that we've been thinking about it now is, are there other data products we can create that really highlight the physics, that can try to give us potentially the more discriminatory information? So that's how we're trying to approach the problem. I guess on the finite element side of things, we're looking into maybe being able to exploit the modal decomposition. And so can you somehow use maybe a minimum set of resonant modes from a target, and maybe that will help gain you some insight. But beyond that, I don't have a specific kind of holy grail answer, I guess. Tim, do you have anything that you've seen?
Yeah, I think one of the things that we learned from the physics in these models is that if we can make all the phase corrections very precisely in the pre-processing. So when we're doing our SAS processing, we do something called motion compensation, which is where we estimate our location. Then we have the potential to exploit phase information. So right now the classifier essentially divides up the early time and late time portion of the backscattered signal, and it takes a Fourier transform, and then it looks at the magnitudes. When you take the magnitudes, you're stripping a lot of phase information there that has a lot of potential classification information. And we know this from looking at the physics. You cannot, and also the signal processing side of things, you can't, for example, reconstruct the original signal faithfully using just the magnitude spectrum. So if we can get our pre-processing very accurate, then we could potentially add phase information to the classification process. And for example, if you look at, as Aubrey described, one of the things we're looking at is the correlation peak between, as a feature, the correlation peak between a template and some of the data that we pick up using the linear scan. Well, if we can look at that, and I actually believe there's other domains that are more useful for determining this similarity, but if we can preserve the phase information and look at the similarities in other domains using correlation or some other process, then that preservation of phase information can really make the similarities more distinct between your model data or your templates and the object that you found in the field. So if you found a UXO and you preserve the phase information and you do this correlation or template matching, you tend to get much better results. The real challenge there, again, is preserving that phase information.
Wonderful, thank you. One last question for Aubrey, and then we're going to ask you both of you to weigh in on broader questions. So Aubrey, would using a different geophysics tool to get an answer on the shape help you get even better elastics results?
Yeah, so that's a good question. It sounds to me like the question is aimed at kind of fusing these different techniques together, and there's definitely an added benefit to that. So if anything that could give you some information about the shape, you could then go in and at least be able to know whether this is something that is maybe howitzer-like or artillery shell-like, or maybe it's more like a big drum or barrel. And then once you know that, you might be able to now start looking in the template for regions of interest, such as are there any indications as to what the filler could be. And so it could be very informative, I think, combining these together.
Great, thank you. All right, so for the broader questions, I'm going to ask you to weigh in first, Aubrey, and then ask Tim to jump in. A question from Cal EPA. Because the processes you discussed are very technical in nature, communicating the results and the conclusions and recommendations with regulators and the public may be challenging. Will you develop communication and training tools to be shared together with the results of your project?
Yeah, I think that's a great idea, actually. I don't know that it's something that was on our immediate radar, but no, I think that's a very good point. Because again, the end goal at the end of this 5 years is to be able to have this deployable system that's going to be easily used, going to be very easy to use as a user. So yes, that's something that we will do moving forward.
Can I contribute a little bit to that as well?
Yep. Please go ahead, Tim.
I think that for the final end user, we don't want them to have to understand the physics of what we're doing at all. We want someone to be able to basically look at a little map of the seafloor and see there's a blob, and perhaps have a box around that blob through which we've passed all this information automatically. We've extracted the spectral features, we've extracted shape features, we've combined them, passed it through a classifier, and gotten some confidence metric that says, there's a 90% chance that this is a UXO or something like that. So we hope that for the end user, they wouldn't have to understand much of what's going on here. Of course, it's always helpful for people to have an idea of what's going on that can inform how you, for example, perform your scan patterns or whatever. But we hope that the end result will be a very simple data product, simply an image snippet with a confidence saying it's this, some percentage likely that this is a UXO, and potentially what kind of UXO it is.
Thank you both. Tim, you already alluded to this. But I'm going to ask you to weigh in more deeply. How do you plan on implementing this kind of processing in the field, and does it require a completely different concept of operations from a standard surveying operation to perform?
Okay, well, I'm not sure if you can say it's exactly the same as a standard if, for example, you're using a completely different technology. So if someone has an underwater sled with an EMI mounted on it, then yeah, we'll probably be doing things a little differently, because we may have a towfish that's say 5 meters above the surface, and we'll be scanning using a towfish that's elevated above the seafloor. But I don't think if you're thinking in terms of trying to make a underwater survey of what the seafloor looks like, then the operations would be very similar. And the idea would be at least as we've envisioned developing the towfish system so far, that we would have a scanning sonar that looks downwards, much like a multi-beam, only at very low frequencies, so we can look through the sediment. And you would just perform standard linear scans. You'd make straight line paths, go to the end, turn around, and change where the scans are by maybe 10 or 20 meters, and then do another survey, and then move along until you've covered the entire area. It would be something very similar to that. And again, we envision that you'd have some data product that would be easy to interpret, that would flag regions. You'd have a GPS coordinates for an object, and some confidence that would say, this is probably a UXO or probably not a UXO. And you'd have visual information as well, so that the operator could make their own personal estimate as to whether or not it's a UXO. And of course, any of these systems would require some degree of expertise because you're dealing with a new type of data product. I don't think a lot of people are used to working with low frequency imagery, for example, but the human brain is an amazing classifier, and if you spend some time just looking at low frequency images for objects, it's something that can easily be done. It's just like looking at a side scan image. When you first look at a sonar side scan image, it may be confusing at first, but once you've used them a few times, then you start to be able to interpret things very easily.
Thank you, Tim. Aubrey, would you like to add to this?
I actually think he covered that very well. So.
Wonderful. So let me ask you a question then. You focused on low frequency acoustics. What about other sensor modalities? And do you have concrete plans to integrate these into the tow body?
So I think that's something that we're going to look into. Again, there's going to be the tow body design as it is right now is going to have some open ports for both data and other possible sensors. So again, I can't answer that concretely right now, but it's definitely something that we are going to be looking into. But you could also envision, even if we don't end up implementing sensors on board this tow body, you could envision, as Tim had kind of alluded to, right, is going forward with this tow body, acoustic tow body, as a piece of a bigger operation. So you could have then another separate body that's out there doing the magnetic side of things. So it could come into play together with another vehicle.
Wonderful. And one last question very quickly before we wrap up. You mentioned that there were a number of field experiments conducted over the past few years. Are the data from these field experiments available to the public?
Yes, they are. So at least for the Pondex 10 data, that's available, and the T-Rex 13 data is also available. The Bayx 14 data, which was in that mud environment, is currently still undergoing the processing, but we hope to get that also through the public release process, and we'll eventually have that available to the public. So again, you can contact myself, and I can put you in contact with Dr. Kevin Williams to get that data to you.
Wonderful. And Aubrey's contact information as well as Tim's contact information is included on this slide, and you can download a PDF copy of the slides from the website. With this, I'd like to thank Aubrey and Tim for doing a wonderful job. Our next webinar is on Thursday, March 24, and will feature presentations that will highlight Department of Defense efforts on cadmium and chromate elimination. This webinar will provide an overview of implementation plans and strategic roadmaps from 3 DoD depots. Registration will open for this webinar shortly, so please make sure to visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webinar. Thank you so much for your time.